So first off, I want to thank the organizers for inviting me here today, and also thank them for organizing this wonderful workshop. Today I'll be telling you about very recent work in the Doyle group here at Harvard on laser-cooled calcium fluoride molecules trapped in optical tweezers. So for this audience, I don't have to give too much of a motivation. So it'll be very brief here. Essentially with molecules, because of their very rich internal structure, you can get many new features, which can be very useful for a lot of applications which we have already heard about, ranging from precision measurements to collisions and chemistry in the ultra-cold regime, to quantum simulation and quantum information. And for all these applications, we want to go to very low temperatures, and if possible, go to ultra-cold temperatures because in this regime, we can, for example, trap these particles, hold on to them for long periods of time, and also control them fully, both in their internal degrees of freedom and also in their motional degrees of freedom. And we hope that, at least in the near future, we'll be able to gain the same amount of quantum control over molecules as we have with atoms. For example, seeing single particles in large quantum many-body systems, or even controlling every single particle using, for example, rearrangeable optical tweezer arrays. In the systems, one can envision building up large systems, one particle at a time, from the bottom up. So outline of today's talk, I'll tell you about how we load single molecules into optical tweezers, which are formed by tightly focused laser beams. Also how we detect them with high fidelity. I will also tell you about how this has enabled us to observe collisions, namely collisional losses between calcium fluoride molecules inside one of these traps. I will also tell you about very recent results from the past few weeks where we can now take single calcium fluoride molecules in separate tweezer traps, merge them, and observe what happens. But before I get to tweezers, we first need cold molecules. As you have heard over the past 2 days, there are many ways in which we can make molecules, ranging from stark deceleration to cryofuges, to taking two ultra-cold atoms and coherently assembling them via StirRap. Of course, I'll be talking about laser cooling of calcium fluoride. And in this approach, essentially, we follow what has been done in the past 2 decades, 2 or 3 decades with ultra-cold atoms. We use photons to slow and to cool these molecules down. And the practical starting point of these experiments is a magneto-optical trap, which is loaded from a source. One of the key features of direct laser cooling is that it can be extendable to many classes of molecules, including complex polyatomic ones. Of course, this turns out to be a challenge, as we have heard from many speakers. We have to figure out how to plug all the leaks. I'll go rather quickly through this because we have already heard from Junyi and Dave DeMille and Nick and Mike Tarbit earlier on this problem. So simply by picking the right molecule, for example, calcium fluoride, we can suppress this vibrational branching. And relying on selection rules, we can also plug the leaks in rotation. But even after all of that, if one were to wanted to create a magneto-optical trap, there's still the problem of dark states, which we have heard about, and there are various methods that we can destabilize these dark states, including polarization switching, or maybe using more than one wavelength. There's another problem with molecules that rise from the large density of states. And the problem is that how do we start off in the states that we want? So one approach that we use is to start with a buffer gas source where molecules first thermalized with a buffer gas of helium-4 held at 1.5 Kelvin. And using this method, we can produce very bright and slow molecules in the states that we want, which is the electronic ground state, ground vibrational state, and the first few rotational states. So I won't go through all the details that lead up to the MOT, but putting together a buffer gas source, slowing of the beam, which is technically actually quite difficult, and all these ideas that I've mentioned, one can create a magneto-optical trap. It's first demonstrated in Dave DeMille's group with strontium fluoride a few years back. And that really is was a milestone in laser cooling molecules because it provides us a practical starting point. And in the years that follow, magneto-optical trapping has been demonstrated in Mike Tarbit's group at Imperial, here at Harvard, and also in Junyi's group for YO. So how do we get from a molecular MOT to optical tweezers? So as you have heard from Mike Tarbit, in these magneto-optical traps, by suitable intensity ramps, we can get fairly close to the Doppler limit. We can also have large number of molecules, 10 to the 4 to 10 to 5 molecules, at least large in the sense of loading a few optical tweezers. The main problem, however, is that the density of molecular MOTs are not high, at least compared to atomic MOTs. And one thing to remember is that optical tweezers are formed by focused beams of laser light, and we focus it down to near the diffraction limit, which means that they have a size on the order of microns. This means that the trapping volume typically is on the order of 10 micron cubed. On the other hand, a typical magneto-optical trap is on the scale of a millimeter. So I'll do the math for you, but if one were just trying to catch a molecule out of the MOT, in order to have near unity probability, one would need densities on the order of 10 to 11 molecules per cubic centimeter. So we're about 5 to 6 orders of magnitude away from the simple direct capture. So how do we bridge this large gap in density? So we rely on a very simple idea that can lead to very large enhancements in density. And this is to have laser cooling working also in the presence of a conservative trap. In this case, for us, it's a optical trap. So let me show you how this works. If you have a conservative trapping potential, if a particle starts outside the trap, it will essentially go through the trap because energy is conserved. However, in the presence of cooling, in the case where cooling actually works somewhere inside the trap, the particle can dissipate its energy and get stuck. And one can then start accumulating particles and thereby increase the density. Of course, there are a few requirements here. First off, the temperature that is achieved with cooling inside the trap has to be very low. Well, it has to be low compared to the trap depth. So either you have very deep traps or you have very low temperatures. More importantly, you need laser cooling to work inside these traps. Typically, we operate with traps that are on the order of a few hundred microkelvin. And if you convert it to frequency units, this is similar. This can be a few times the excited state line width. So in this regime, the actual states, ground states of the molecule can actually be significantly affected by the trapping potential, which can interfere with cooling. But at any rate, let's go ahead and look at how we can go to low temperatures, since practically there's with limited laser power, we can only make traps a certain depth. So as we've heard from Junyi, from Dave DeMille, and also from Mike, there are ways that we can get cold, much colder than the Doppler limit, which is 200 microkelvin in the case of calcium fluoride. You've already heard about gray molasses, where one can rely on a Sisyphus-like effect to go to low temperatures. So about a year back, we implemented the scheme, which was first demonstrated in the Imperial group. And what we found was that, in fact, we can make this gray molasses scheme work also inside these deep traps. And because of the effect that I just told you, we can vastly increase the density inside these optical traps by roughly a factor of 10. And as you have heard, there are ways that can get even colder compared to just simple gray molasses. We borrowed a page from Alkali Atoms where we create coherent superpositions that are dark only when the molecule is slow. This was explained earlier, but the idea is, I'll go through this quickly. The idea is very simple and can be captured in a 3-level system. So here we have 2 ground states, A and B. And if you stare at it, you can see that this superposition state, A minus B, is actually dark to the light because the 2 arms, the 2 drives actually coherently interfere because of this minus sign. So as long as we make this dark condition dependent on the velocity, we can avoid recoil heating once the molecules get slow. And this can simply be achieved by sending in these 2 arms at different directions. So we implemented this, and in free space, this gets us rather cold by another factor of 10. But more importantly, this also works inside optical traps and gives us roughly another order of magnitude, getting to somewhere near 10 to the 8 when we first implemented this. So it gave you many different numbers. So just to put this on the map, since the first MOTS that were created with strontium fluoride, temperatures over the last 5 years, the temperatures have essentially gone down by roughly a factor of 1,000, well below the Doppler limit by now. And the densities have also gone up. And here, by implementing laser cooling, in combination with a conservative trapping potential, we can actually now push actually beyond 10 to the 10 per cubic centimeter. So the other thing that being able to laser cool inside optical traps by you is that we can also detect molecules much more efficiently. So essentially by applying lambda cooling to optically trapped molecules and collecting the scattered fluorescence, which we call in short lambda imaging, we can collect many more photons than simple resonant excitation of the molecules. And when we first tried it out about half a year back, we were very encouraged because it seemed to suggest that it could make possible single-shot, non-destructive detection of single molecules inside an optical trap. So at that point, we realized that we actually had all the ingredients that were necessary to create single molecules and detect them inside optical tweezers. We had a way of overcoming the low densities in the MOT, and we also had the ability to see, or we should have the ability to see single molecules. So in the next few slides, I'll tell you specifically how we get from this large millimeter-sized MOT down into a micron trap. So we actually follow a 2-step loading process where we go through an intermediate, relatively large optical trap. So first we take the MOT that is about 1.5 millimeters. We apply lambda cooling to enhance density inside this 40 micron 1064 optical trap. Then out of this relatively large trap, we try to pick out single molecules with even smaller tweezers that are about 2 microns. Specifically, in the loading step, we ramp down the intensity of the large optical trap while ramping up the tweezer trap. And very importantly, we have to leave the cooling light on so that the molecules have a chance to get stuck inside. So after some work and after many averages, we're very happy when we saw a first signal of molecules ending up where we expect them to be, or where the tweezer trap is. Of course, this is not quite enough. We want a little bit more. We don't just want molecules inside the tweezer trap. We want exactly either 0 or 1 molecule. There are many reasons for that, but one of the practical reasons is that if you know that the occupation is either 0 or 1, in a single shot, if you saw a bright spot, you don't have to think about what the occupation is. So how do you tell how many molecules are in the trap? We decided, before I tell you how we actually figure out how many molecules are in there, we decided that we'll just try out a way that could clean out multiple occupancies. Similar to work with atoms trapped in optical tweezers, we tried to extend the cooling light, which is near resonant, by a few milliseconds, in the hope that light-assisted collisions will clean out occupation numbers that are 2 or higher. So we applied this, and then we tried to figure out whether now we have single molecules. So to do that, we actually have to start looking at individual images. So the way we do this is that we take a region of interest in our image where the molecules are, and we sum up all the counts inside this region for every single realization of the experiment. Then we put this count, these counts, we put it on a histogram, or we make a histogram out of it. And when we do that, we see 2 features. One that is centered about 0, and then a secondary feature that is a little bit displaced. Now, this is not sufficient to tell you that you have single molecules. All it tells you is that sometimes you have nothing because you have a 0 peak. So to check whether we have single molecules, we varied the loading rate. So we kept reducing the initial number in the MOT. And we looked at how these histograms evolved. So when we reduce the loading rate, we find that the secondary feature decreased in amplitude. But importantly, the peak position did not move. And this actually tells us these are indeed single molecules. The reason being that if we had more than 1, as we reduce the loading rate, the mean would actually move lower. So knowing that we have single molecules, we went ahead to try to go more than, to try to scale up the system to more than 1 tweezer. And we do that simply by using a acousto-optical deflector to generate multiple traps. This device essentially deflects the beam based on what RF frequencies you put in. So we can have a single trap, and we'll see molecules trapped in 1 position. Or we can put 2 traps, and we can move them around even dynamically. Limited by power currently, we can get up to 5 traps. And with some improvements in the imaging, we can start seeing very resolved images of these single molecules. So shown here is an average image of 5 tweezer traps with single molecules. And to give you a sense of the signal to noise shown here is a single shot image, and you could already tell which traps are filled just from 1 shot. We can be more quantitative, and we can look at the histograms, and we can, and from the histograms, we find that a few months back, we could have a detection fidelity of around 93%, which we have improved now, as I will tell you in a little bit. So one can ask, is it possible to actually see collisions in these tweezer traps? I told you that we just extended this cooling light for a few milliseconds in the hopes that it would clean up multiple occupancies. So after we got the tweezers, we decided to try to resolve the dynamics of possible losses when we have more than 1 molecule. So just to slow things down a bit, we enlarged the trap to reduce the density. And we wanted to see whether two molecules inside a trap would decay faster than one. And we need to slow down the dynamics because our imaging actually takes quite a bit of time. It takes on the order of tens of milliseconds, while collisions in principle could be much faster than that. So as you have heard in the previous talks, typically if you want to look for two-body loss, you try to look for some sort of, well, second-order loss. You want to look at non-exponential decay. Here we have a slightly different way of trying to tease out the signal. Instead of looking at this, we actually look at the histograms. And by waiting for long times, we can isolate what a single molecule plus zeros look like. And then we can go very far out in the tails where we know that there should be no signal coming from the single molecule feature. Then just by counting specifically in these high count regions, we can be sensitive to occupations that are more than one. So here, to look at possible collisional loss, essentially we load the tweezer, which can have, for example, 0, 1, 2, 3, 4 molecules. We hold it for a variable of time, with and without cooling light, and see if we can observe decay. And when we did this, we find that whether we have the cooling light or on or off, multiple molecules always decay faster than single molecules, which can be whose lifetime can be obtained just by summing up in the region that corresponds to a single molecule. Of course, when we have near resonant light, the losses are about an order of magnitude faster. And assuming these are two-body losses, we can actually extract the two-body loss coefficient and also the inelastic loss cross-section. And these are in the 10 to the minus 10 and 10 to the minus 9 centimeter squared range. So looking at histograms, different regions in histograms is actually a little bit difficult. And also, just looking at the tails, we don't quite know whether these are single molecules. We don't know whether these are 2 molecules, 3 molecules, or 4 molecules. Where they contribute actually depends on the loss, and it's a little bit of a complicated problem. So why not make use of the new platform that we have, which are single molecules trapped in optical tweezers to study collisions? Namely, why not load 2 molecules in separate traps and then just merge them together and see how they go away in time? So before we start doing this, we have to improve our detection a little bit. So after some optimization, now we can get essentially 97% detection fidelity, which is sufficient for us to have non-destructive detection essentially at the 90% level. And we can check our non-destructive detection fidelity simply by first imaging the molecules and then re-imaging and comparing the 2 images. And currently, a large portion of this fidelity is actually just limited by collisions with background gas. So with this better detection, we moved on and tried to see whether we can detect non-destructively and also move the molecules after we have measured what their configuration is. So this is what I'll call detect and rearrange. So instead of 5 traps, I'll work with 3 traps here. So each trap can be filled or empty. So there are a total of 3 bits of information, and there are 8 possible configurations. Here, the circles mark the case when we have an occupied trap. For example, in this case, shown 101 would correspond to this row. So for this detect and rearrange test, what we do is that we first take a snapshot of these tweezers to identify which of the 8 configuration the system is in. For example, it's in this 101 configuration. And we'll implement a simple scheme where we just move all the molecules to the right. So essentially, we just shuffle everything here to the right. Of course, the movement depends on what configuration the system is in, so it depends on the first measurement. So in principle, in the ideal world, the result should look like this, where all particles start stacking up from the right, 1, 2, or 3, or 0. So we went into the lab after some optimization. We were happy to see that experimentally this does work out fairly well. And it might be hard to see, but this is actually experimental data. And the color scale here actually corresponds to something like 90%. And to read this table, essentially each row is conditioned upon the result of the first measurement. So great, we can non-destructively detect to check the occupation, and we can move them. So let's try merging two traps with single molecules to look for possible collisional losses. So here, again, we have 3 tweezers. And what we'll do now is that we'll keep the central tweezer fixed. And what we'll do is that we'll move the rightmost trap into the center trap. So we'll always merge to the center if it is filled. If it's not filled, then we'll move the left one into the center trap. And if both are filled, we'll always prefer the right. So in this experiment, essentially after the movement process, in the center row you will see either 0, 1s, or 2s, which is marked here in red. And now the next step is quite simple. We just wait and see whether the doubles go away. And of course, we know when we have doubles because we have measured it first in the first step. So if there are collisional losses, we'll see that the doubles will go away quicker than the singles. There's a slight problem with this at this point, because if we were to detect the system, we wouldn't quite be able to tell 2s from 0s, because our imaging time is actually much longer than the light-assisted collisional lifetime. So we implement one more step where we just reverse this merge to the center step. We just split it back apart. And if we tune the traps such that they are balanced, then, for example, in this configuration of 020, there are 4 outcomes from the splitting process. It can be 002, 020, or 011. And 2 of these actually survived the detection procedure. So then we have a fairly simple scheme of measuring lifetimes of 2s. We know that they're 2s based on the first image, and we find out what fraction of those shots will give us 2 in the end, and how it varies as a function of hold time. So this is fairly preliminary data. So looking at all these possible channels where we can have 2, we do indeed see that this fraction decays as a function of this hold time. And to check that this is not due to technical heating during the movement process, we also have available in the data set the times when we only loaded 1 molecule, so we can look at the singles lifetime too from the same data. And we do see that the singles essentially have a very, very long lifetime compared to this tens millisecond time scale. And this is preliminary, and this actually is an updated plot from, it's about half an hour old. And this actually is a zoomed in region in between 0 to 80 milliseconds. And with that, I come to the summary and outlook. I have told you some a bit about how we cool and load single molecules into optical tweezers and how we detect them with high fidelity. I've shown you some results beyond looking at one molecule, beyond single particle. I've shown you how by looking at different regions in the histogram, we can actually see collisional losses. And I've shown you some preliminary data on non-destructive imaging and rearrangement of tweezers and merging of tweezers to look for collisional losses. All these measurements are actually done in a single rotational state. It's in the first excited rotational state, but it is not hyperfine resolved. So that's something we would like to explore fairly soon. And by implementing optical pumping, just like what Mike Tarbert has shown, we should be able to isolate a single quantum state, and we can use microwaves to transfer into the absolute ground state to explore this, what happens there. All of the techniques that I have told you about in this talk are in principle extendable to other laser coolable molecules. And it's pointed out by Isaiah Wimberger and also by Ivan Kozyriev and collaborators. There are actually many molecules, including complex polyatomics and triatomics, where this is possible. We have already heard of some of this on triatomics from Nick earlier. And in general, with these new molecules, for example, triatomics, the new modes can lead to give you some favorable features. For example, bending modes in the triatomic can be particularly good for EDMs or maybe for detection of dark matter. And going larger to, for example, symmetric top molecules, these new rotational modes about the symmetric top axis actually provide us doublets that can be very good for applications in quantum information processing. We just put out a paper on this together with Phelan, who's in the audience, and Ivan and John. And Phelan will be presenting a poster on this later today, so go talk to him if you're interested in this. I also want to advertise that there's ongoing work on triatomics in the Doyle group on laser cooling, both in CaOH and also YBOH. And there will be posters later in the day. With that, I come to my final slide. I want to acknowledge the fantastic team of people that have made all these results possible on the CAF experiment. Loic here, Yi Cheng, and also Sean. I think they're all in the audience. And there will be also a poster on CAF later. This is also a collaboration with Wolfgang Ketterle, Conquin Ni, and led by John, who's here, and probably up there. And with that, thank you for your attention.
Thank you very much, Sean. It's awesome. Very nice results. Question, one or two? Please.
What about interactions during the splitting? They could bias the detection scheme. I guess you neglect them for now. You just keep they're not there, but that's
Yes, so
not so clear, right?
yes, so for strong interactions, this.
Interactions during the splitting process.
Interactions between the molecules?
Yeah. Well, when you go from
Just clarify.
yeah, but when you go from two molecules to the split trap.
Yes.
I mean, I understand your heart and the dipole trap is not as confining, so interaction should be weak. But I think it's clear what you assume in the detection scheme is that interactions are non-existent. Because if there would be interactions, that would clearly bias the detection.
Yes. For example, in the case of very strongly or infinitely repulsive interactions, they would essentially always split into one and one. So here in this case, we're assuming that the interactions are small compared to the temperature, which should be true in our case.
Probably anyway not a quantum. You probably just thermally activated hopping over the
Yes, and we also, yeah. Yeah, so there's also the issue of quantum statistics, which should not be a problem here because we are actually in many motional states. So we don't get 2002 for our bosonic molecules all the time.
And one more? No? Thank you. Go ahead, Anya.
So you just mentioned that your motion is quantized, right, and you occupy many motional states. Does that affect the collision process?
We are essentially in the classical regime in terms of the motional states inside each tweezer trap. So the temperature inside the tweezer trap is actually much higher than what we can achieve with cooling in free space. It's on the order of tens of microkelvin to maybe a little bit above 100 microkelvin. So it's classical in that sense.
In your conditional experiment, did you extract the rate out? Or are you able to extract the rate or not?
So for the data that came from the histograms, we did extract two-body and elastic loss cross-section, but not for the latest data because we haven't measured the temperature or the density yet.
Okay, then move on. Thank you very much, Lawrence.